Hello, my name is Ignacio Solis Camacho. I am going to present to you belong to encrypted code present with the Xbox, the P layer, and the key shells. Okay, um, we in this code we have to first declare an declare the identity. In this way, it will be processed. Um, Two, we have vectors from the 9 to 0. In this case, because there are 10 the 10 switches which it is the 18 bits vectors. Then we have a plenty in the switches with it is vector from 7 to 0, and the 8 switches which are the 64 bits. Then we have a display which are the ones we have on the FPGA target. And then we have a semin which is a vector from 0 6 6 to 0. In this case 6 to 0, and this to say the 7 bytes which are the last bits or the target. Finally we have a vector from 3 to 0, and these bits that are you're going to from the Xbox layer. Now, in this part, we declare the key vectors, which are the coins 80 bits, the plain text, and which are the 64 bits, the rounds of the XOR output on the field rounds and the output of the Xbox layer, the permutation layer, and the changing subcaps. And here the run signals from round number 1 to round number 32 are all shown, which will be shown later in the 64 vectors here. Okay. Now and in this case we have a 4 bits vectors that is the from 3 to 0 here. This is to declare the class R that we are occupying in the Xbox layer. In this case, we will be using 0 to F. Now, here we have the Xbox layer, which is a nonlinear operation. In this case, we are using the table that we have for the case of 0. We are going to have a letter C for here 0 letter C. For 1 equal to 5, and 2 equal to 6, 3 equal to B, 4 equal to 9, 5 equal to 0, and so on, and ultimate research F equal to 2. This will begin the B in hexadecimal value. Okay, for to encrypt a message, the player takes the plain text message and divides into 128 bits blocks in the series of runs of the cryptography operation and defined by the encryption standard 12 uh, the advanced encryption standard algorithm to transform each data block into a encrypted block. This process is repeated for each block of the data until message has been encrypted. To decrypt the encrypted message, the player performs the research process, is take the encrypted blocks and process then draw a series of rounds of research cryptography operation to obtain the original plaintext message. Okay, okay. Here, point 3. Xbox or um, Xbox output is the output signal on the Xbox layer in each iteration of the loop. A bit is taken from the Xbox output signal and assigned to the corresponding position in the player output signal using a format that rearranges the bits according to a specific permutation. Okay, the present encryption is currently important in relation to the Xbox layer, the permutation layer, and the key schedule for severe regions, data security, confidentiality, um, and integrity. Uh, for example, in data security, present encrypted is a widely used cryptography algorithm that ensures the security of data by encrypting effectively. The Xbox layer, the permutation layer, and the key shadows are essential components of the algorithm that contribute to it is robust and resistant to attack.
Hi, I'm going to talk about the key runs and how it works. Previously, my partner just talked about how we implement this present cipher in each HDL code, but now I'm going to show you more about how the key runs was obtained by. So let's begin talking about why are these keys important. These 32 keys that we are going to generate. These key rounds are used to generate a set of unique subkeys from a master key. These subkeys are essential for each round to obtain encryption algorithm in this present cipher, and we generate it in a way that they are independent and they are not related to each other. This means that each subkey it contributes to the security of the encryption. Now let's begin about security. By using unique subkeys in each run, in encryption round, in these 32 rounds, the key rounds significantly will increase the security of the algorithm and then provide you data information. And this diversification of keys makes it more challenging for the attackers to try to decrypt the message without knowing the correct key. And now we have the key. We have the 80 bits key, and in order to get these round keys, we use this application and we generate it in Java. We have problems making this code in PHDL because they don't generate it like it was too much information for the FPGA. So we decided to get only the round keys in Java code, and then we implemented into the VHDL code. So we only just copy the correct values of the round keys. So first, in this code, we generate each round. We use this for to in order to delimitate to only 31 rounds. It means 32. But and then we program this for use these more bit significant bits, and then we rotate it to the left in order to get these final runs that you can appreciate in the next in the image that is in the right part. This random key, and we generate this in, and after all of this process we generated to the BHDL code. And but now we are going to use this plaintext with the string zeros and the key, and we are going to XOR all 32 rounds. And after all this process, we have this already cipher text that is already encrypted. And now that we explained all of this process, this present cipher, we just need to get the pin planner correctly in a way to get this correct ciphertext output. So we choose to get only four displays, and we are going to add a clock to generate this the cipher text that is going to show you 16 bits. We're going to show you for each bit for a display. It means that we have this clock in order to get this bit by bit that I will show you for. Like in the next slide, we're going to show you how this works. And now, as you can see, these are the outputs with the clock that we work for the ciphertext. That is going to be to the right, to the left. The ciphertext is completely correctly with the output that we obtained, and with this we successfully work this ciphertext.